All right, so now let's go on to some examples. Example 1 is just the example we've been using to talk about how to find, how to set up your data and how to find expected values. So I've set this up in an Excel file. This is just exactly the same way we set it up previously. I've just found the row totals as well as the column totals. And now I could start on my hypothesis testing. So first things first, step 1. Our null hypothesis should say something like this, that the proportions of satisfied and unsatisfied people, I guess, adults, for Democrats should be the same as for Republicans. So the proportions of category 1 and 2 of satisfied and unsatisfied, I'll say voters, should be similar for Democrats and Republicans. So the alternative hypothesis is that at least one of those proportions will be different between Democrats and Republicans. All right, step 2. Step 2, we'll just set our alpha to be 0.05. And we know that because we're doing chi-square hypothesis testing, it's one-tailed. Step 3, you might want to draw a chi-squared distribution for yourself or just in your head and sort of color in that alpha part and try to think, okay, I want to find my critical chi-square. In order to find the critical chi-square, I need to find my degrees of freedom. And my degrees of freedom is going to be made up of the degrees of freedom for category, as well as the degree of freedom for population, right? There's two populations, so it's 2 minus 1. And you could also see that as the columns, 2 columns minus 1. You don't count these total columns. Those aren't real columns, nor do you count this total row. And the degrees of freedom for number of categories is we have 2 categories, satisfied and unsatisfied, minus 1, right? And that corresponds perfectly to number of rows, minus 1. And so the degrees of freedom here is going to be this times this, right? So degrees of freedom for category times degrees of freedom for population. And that's just 1. So what's our critical chi-square? Well, that's going to be found by chi-inv. We put in our probability as well as our degrees of freedom. And we find 3.84 is our chi-square, critical chi-square. So we're looking for samples that represent populations, sample chi-squares that are larger than 3.84. So step 4 looks something like this. So in order to find our sample chi-square, what we need to do first is find our expected values. So here we have observed frequency, right? What we need to do is find expected frequency. So I'm just going to copy and paste this down here so we don't have to keep scrolling. I'll also bring this up. And so I'm going to write the table here for observed frequency, but I'm going to create the same table for expected frequency. Although now I have to delete all these guys. Okay, so when I look at my expected frequency, I need to find out what's the general rate and then multiply it by however many, in this case, people I have in that sample. So the general rate of being satisfied is 1,316 divided by 1886. So that's the general rate, and that's about 70%, right? I'm going to take that and multiply that by the total number of Democrats. Now, this part, I want to keep that the same, and I want to keep that in the same column. So I'm going to put a dollar sign in front of the D to lock down that column. And here I'm going to put a dollar sign in front of both the D and the 21 in order to lock down this actual cell. Because here's what I'm going to do. I'm going to actually copy and paste that over here. And if I look at this, then what I'm doing is I have this same rate, again, the rate of being satisfied, but now it's multiplied by the number of total Republicans. And then I'm going to take that cell, copy and paste it down here. And here I see that now I have the rate of being unsatisfied, and I need to change this to that. And here I have the rate of being unsatisfied, and I'm going to multiply it by total number of Republicans. So these are my expected frequencies. Notice that the totals still add up to be the same, right? And usually it should. There might be some slight discrepancies, but that will just be because of rounding error. So they should still be pretty close. So now we have observed frequencies as well as expected frequencies. And now I need to figure out my chi-square. My chi-square is going to be made up of observed frequency minus expected frequency squared divided by expected frequency. And I'm going to need to find that for Democrats and Republicans, as well as satisfied and unsatisfied. And then add up all of these cells, right? So I'll say grand total, and I'll put that over here. Okay, so let's find the observed frequency minus the expected frequency squared divided by expected frequency. And I could just copy and paste that here because Excel will just move everything down. Then I can take this, move it over here, because Excel will move everything over to the right. Ta-da! All right, and the grand total for all four of these is going to be 547.18, right? And so my sample chi-square is quite large. Quite large, right? And so do I reject my null hypothesis? Indeed I do. And we can find the p-value. So here I'll put chi dist in order to find my probability. Here it is. Degrees of freedom is going to be 1. And that is a very, very, very small p-value. So this is a pretty radically different population that we stuck in there. All right, and if you want to put in step 5, you could say reject null. Great. Example 2. Consider this data on pesticide residue on domestic and imported fruits. Does this data fit the conditions of a chi-square test of homogeneity? Regardless of your answer, conduct a hypothesis test. Now be careful. Here, although you see columns and rows, these are not the columns and rows you should be using. The columns are actually okay. Domestic fruits, imported fruits, we could consider those two to be the different populations we're interested in. But the rows actually don't show the different categories. It shows sample size, percentage showing no residue, and percentage showing residue and violation, right? So what we should do is we should actually transform this data into sort of the correct setup. Okay, so here you could just pull up a brand new Excel file. I'm just going to use sort of the bottom portion here. And here's what we want. Oh, excuse me. Here's what we want. We would like it to be set up so that we have the two populations up here, and we have the different categories here. So the categories are probably going to be showing no residue, showing residue and violation, but one of the things I notice is that these percentages don't add up to 100. So there must be some other category that we're missing. So no residue, showing, so residue in violation of the law, so I guess that's really bad. And maybe there's just one where it's residue, but not in violation. And you sort of have to figure that out from the data that they've given you. But they do give you the sample size, 344, as well as 1,136, right? So this is the total. The question is, what are our observed values? Well, in order to find the observed value, all we have to do is multiply the proportion, so 44.2% times the total, right? And here, I want to lock down that row. Now, residue in violation, what I have to do is I have to change this percentage. So the percentage is 0.9%. So that's 0.009, right? Because that's what we would read as 0.9%. And so what's sort of left over? Well, the leftover percentage is 1 minus 0.442 plus 0.009. Right? So that's sort of everybody else. And that's, I guess, the number of fruits that are not in violation but still have some residue on them, some pesticide residue, times this. And so when I add them all up, I could check, and that's 344, right? So I've done my proportions correctly. Now, right away, we could see that we're actually not meeting the conditions for chi-square. If you look at this cell right here, that only has 3 fruits in it, right? Even if we round up generously, it's 3.1, right? So there's only 3 fruits. Remember, expected frequencies have to have at least 5, right? So here the observed value is pretty small. Okay, so, but it said go ahead and do hypothesis testing anyway. Okay, fine. You shouldn't do this in real life, but for the purpose of this exercise, let's do it. Okay, so now let's find the proportion of imported fruits that are observed to have no residue on them. So that's 70%. So 70.4% times this total, and that's almost 800 fruits. Also, we have those that have residue in violation, so 0.036, that's 3.6% times 1136. So that's about 41 fruits. And then I need the leftover percentage, right? So that's 1 minus 70%, 70.4% plus 3.6%, right? that percentage times the total. And that's 295 fruits, right? So first notice that these seem like there's way more of these imported fruits than domestic fruits. But that's because the totals are different, right? So it doesn't necessarily mean that, whoa, imported fruits, they have so much residue on them, right? That's not necessarily what it means. Right now it's hard to compare because these have totally different, totals, right? So it's helpful to find the row totals as well, because that's going to help us find expected value, expected frequency. And so that's adding these rows together. And we have a total of 1,480 fruits, domestic and imported all together, right? Once we have that, then it would be easy for us to find expected frequency. And expected frequency we could basically set up in a very similar way. Except I'm just going to clear these out. All right. So what is our expected frequency? Well, the expected frequency is generally how frequent, what's the proportion of no residue over all the fruit, right? So that will be this row total divided by the grand total. That's the general rate. And we want to lock down this row. There we go. We want to lock those two values down because that's always going to be the rate for no residue, times the actual number of domestic fruits. All right, so we get 221. And here we do the same thing, and I've just copied and pasted across, and Excel will just magically figure out what to do. It's going to go to the right. So this is the rate of no residue over total fruits times the total number of imported fruits. All right. Then we find the rate of fruits that have residue but are not in violation, which is this total over the grand total. And I'm going to lock down those values. Oops. And then I'm going to multiply that by the total number of domestic fruit. And then if I copy that over, that should give me the total number of imported fruits, the expected value of imported fruits given this proportion. And finally, the proportion of fruits with residue in violation, so a lot of pesticide residue, that would be this total divided by the grand total. And I'll lock that down. Times the total. And here, what we can see is if we sum these three expected frequencies together, we should get something similar to 344. And indeed we do. And here we should see 1136, and indeed we do. Great. So once we have our table of observed frequencies as well as expected frequencies, now we can start to calculate for each cell the observed frequency minus expected frequency squared as a proportion of expected frequency. So O minus E squared as a proportion of expected frequency. So I will copy these cell labels. So observed frequency minus expected frequency squared divided by expected frequency. And just going to copy and paste all that. Let's check one of these. This one says the observed frequency minus expected frequency squared over expected frequency. And when we add all of these up, we get 102. But we've forgotten the different steps. We forgot to make a decision stage. So let's go ahead and do step 3. So the decision stage will be our critical chi-square. And our critical chi-square is found with degrees of freedom of the categories times the degrees of freedom of the populations multiplied together. So the degrees of freedom for the chi-square. So categories minus 1 is 2. Population minus 1 is 1. So the degrees of freedom is just 2. So our critical chi-square is chi-inv. We put in 0.05 as our desired probability. Our degrees of freedom equals 2. And we get 5.99. And when we see that our chi-square is much larger than that, so we would reject our null.